So let's just go back to this potential step problem that we started last time. As we mentioned at end of this last lectures, that there will be a total reflection if this energy, capital E, is lower than this V0, this height of this potential step. And there is something really strange going on, namely, it looks like we have a solutions telling us that this wave function really decay exponentially inside this potential step, but somehow this reflection probability is really 1, which means that you have the total reflection. So what is going on? So this is the so-called total reflection. Even though you get a total reflection, which is reasonable from our classical point of view, but still you get finite transmission coefficient. What is going on? So it looks like something is actually leaking to the inside of the potential step, but then you get a total reflection, so something is extra. This transmission coefficient is not 0, even though this total reflection, meaning this reflection coefficient is 1, but the total reflection, this transmission coefficient is non-zero. So what is going on? So we say that this is called a quantum tunneling. The part of the wave function penetrates into this classically forbidden region. And this phenomenon is called quantum tunneling, but of course this is not the real tunneling because this barrier is actually semi-infinite wide, so that this particle cannot really tunnel through the step because the step is really extends over to this plus infinity, so something cannot go out, but something really penetrate inside this potential step, but it doesn't go through this step, but it penetrates. So the only explanation, as I mentioned, is that quantum mechanics allow some virtual state inside the barrier. So let's say in virtual state, I mean this is not the real state, meaning we cannot really measure and detect this virtual state. So now this virtual reality is a fashionable term, so you can actually wear a really fancy glasses and play some video games which mimic the reality, so-called virtual reality, but here is really virtual, meaning we should admit that some wave functions should really penetrate inside this potential barrier, but that cannot be detected, as I mentioned already, in any measurement. So the reason why we cannot detect this virtual state is that if you calculate this probability current or flux on the right, and this is 0, because this wave function is really a real value function. So when you take this derivative of this u respect to x, and also following this standard definition of the flux on the right, and we'll get the exact cancellation because u and u star is the same. So if you take this derivative du dx and du star dx, you get the same, and u star are also the same. So you get the exact cancellation between these two terms, and this flux vanishes. And the flux is something that you can measure in the lab, and if you don't get a flux, which means that you cannot measure in any experimental techniques. And that's the reason why we call this virtual state, because it is there, but you don't have any access to know that it's there. And this is the magic of quantum mechanics, that we should allow for some sort of quantum tunneling or penetration of your wave function inside the forbidden area, but then at the same time, there's no way that we know that there is a wave function there. It's like we need to accept that the wave function exists, but there's no way that we know that there's wave function exists. Just because you don't have any way to detect this wave function doesn't mean that the wave function doesn't exist. It looks like we need to accept some kind of idea of a ghost, but it's not a ghost. It's a quantum mechanical virtual state. So this is the essence of virtual state. We should assume the virtual state is really some state that you cannot detect, but you should assume that the states should exist. So this is the first time that we encounter such a quantum virtual state. And by the same mechanism, this virtual state properties, we will see later that there is indeed quantum tunneling effect when this potential barrier is really shows a finite width, and you'll see later that if this energy is actually lower than this potential barrier height, then indeed there is a finite probability that you could really detect the transmission wave on the other side of the barrier. And on the other side of the barrier, this is a real state. So once this particle really tunnels through this barrier, then you could use whatever method that you're familiar with, that you could detect this flux. The flux is non-zero once it penetrates through the barrier to the other side. But then here comes the same magic. So if there's no such a state that exists inside the barrier, how can this particle just come out of nowhere and then penetrate through this barrier to the other side? So we should admit that particle exists inside the barrier. Again, this state is the virtual state, the same virtual state that I mentioned right here. So you cannot detect the virtual state inside the barrier by any measurable method. But you need to accept that this wave function really has ever been inside this barrier. Otherwise, you cannot explain why this particle or the wave just come out of nowhere and penetrate through this barrier if this particle is never been inside the barrier. How can it just go out of nowhere to the other side? So the virtual existence of quantum states is a very important phenomena that you should understand. And this is the quantum tunneling is the foundation of many modern experimental techniques in solid state, such as scanning tunneling microscope, STM, or many other equipment or experimental techniques that you're familiar with. And this phenomena is actually real. So we take advantage of such a quantum tunneling phenomena for a study of surface of an atomic thin layer, for example. So we will talk about this STM and quantum tunneling later. But here I just mentioned that the same concept that come up, and this is the new idea and concept that is different from classical mechanics, namely we should accept certain type of a quantum virtual state which cannot be detected but is there. So such kind of concepts that I just mentioned will be in your midterm, something like that. So how can you explain something which is weird and classically forbidden? So the final remark is this. So this potential step problem shows very sharp jump of the potential profile, and you see that this R and T, this reflection and transmission coefficient, this h bar, or this quantum unit, this Planck constant, h or h bar, is absent. So it doesn't depend on h bar. So this makes us wonder whether this is really a classical or quantum problem. So is it really a quantum mechanical problem, or is just a classical mechanics problem? Because h bar doesn't appear here, but here we like to argue that even though this h bar is not here in the final solution of the reflection and transmission coefficient, but it is really a quantum mechanical problem. So the reason is that we should go back to this classical and quantum limit. So remember in this first chapter, I think, we mentioned this diploid matter wave. So diploid wavelength, lambda, when this lambda is really, really small, even smaller than this minima length scale, which is some kind of lattice constant. And here, this minima length scale refers to the width of this barrier, a, little a. So when this step becomes really sharp, this little a goes zero, meaning this potential height really suddenly goes like a jump from finite value to zero within almost no width or no finite window. So this window over which that this potential drops from finite to zero goes to zero. Okay, so this is really a tiny little window over which this potential profile just suddenly changed. So this is the minima scale of the problem. So this minima scale, little a, when this a is really larger than this diploid matter wavelength, then we say that this is in classical limit, because then you can convert this diploid matter wavelength to the momentum, right? So the momentum is h over lambda, right? right? So which means that you have a very high energy particle, and in that limit, all this discrete energy levels become continuous, and you don't care about this quantized energy anymore. So if you are in this high energy region, then this all energy levels are continuous, and this h bar is not there. But clearly this is not the limit that we are talking about right here, because here A goes really 0. This is really the quantum limit when this deployed matter wavelength is really larger than this minima length scale in your problem. And as A goes to 0, this deployed matter wavelength is really much larger than this minima length scale in the problem, and this really satisfies this quantum mechanical limit. So this is indeed a quantum problem. It's not a classical problem, even though h bar is not there. So we cannot judge whether this problem is classical or quantum simply because h bar is here or not here. The really criterion to say whether this problem is classical or quantum should be based on this criterion, that deployed matter wave, the wavelength of deployed matter wave is when this is much smaller than this minima length scale in the problem, then this is classical, and inverse if this is an opposite limit, and you get the quantum limit. So this is the final remark. Any questions? So if not, let's take a short break. When we come back, we will study a new potential problem, which is potential well problem, and then we will continue to potential barrier problem and quantum tunneling and double barrier, and that will be the final section of the chapter 4. So I suppose that some of you already learned this in your modern physics, but then the purpose of repeating this subject is to really go deeper to the essence of the quantum mechanics. So suppose we have this potential well, and 0 refers to the horizontal axis. The zero energy axis is this x-axis, and the well shows the energy depletion below 0, meaning this energy inside the well is negative. The depth of the potential well is V0, and this well is actually symmetrical with respect to this center of the well. So you immediately see that this potential shows parity symmetry, right? Because with respect to this vertical line in the middle, this potential is really shows the mirror symmetry. Okay, is the same on the negative and positive side with respect to the central part of the well. So then the solutions already based on this parity symmetry tells you that there should be even parity solution and odd parity solution, right? The sine and cosine function should show up, and we will see just a moment that this is indeed the case. So let's just talk about the energy above 0, which means that this energy is really higher than the ground level and higher than this potential well, so that you can expect that this particle can actually pass through the other side of the well. But of course, quantum mechanically, it allows some finite probability amplitude that this wave function of this incoming particle can actually go reflected. So in other words, you may have some probability that this particle can get reflected, even though there's nothing that could become a barrier to this particle, but seems this potential changes, right, in the middle region, so the particle feels some potential difference. Okay, so even though this potential is not a barrier but a well, but quantum mechanically this particle can also get reflected by a finite probability amplitude, and of course this particle actually can tunnel to the other side. So there is a finite transmission coefficient associated with tunneling, not the tunneling but transmission. So let's just define K and Q as before. So since capital E is actually larger than 0, so the energy from this level of the particle till the bottom of the well is really E plus V0 magnitude, right? So because E is the magnitude up to here, the ground floor, you get a basement. So V0 is really lower than the ground floor. So the total energy from the top of the particle till the bottom of the well is really E plus V0. So there are 3 regimes, left, middle, and right. So you could really write down the solution, because in region 1 you get an incoming wave and reflected wave, and with the same wave number k, because the left hand side of the well there's no potential, and in the middle you expect that this particle inside the well shows this sinusoidal solutions with n and b prefactors in front of the e to the iqx and the e to the minus iqx, where q is the wave number inside the well and q squared is given by this value. And on the right, this particle goes through this well to the other side, and with the probability amplitude t times this right moving plane wave e to the ikx. So this is your ansatz, and you plug into this time independent Schrödinger equation and you look for the solutions with capital R, T, and also A and B with the help of the boundary conditions and from various conservation laws, as I mentioned last time. So you have flux conservation and you have a continuity of your wave functions at these two boundaries, plus minus A, and also the first derivative's wave functions evaluated at these two boundaries should be continuous. So you have many boundary conditions to fix these four unknown variables. And so let's just check this flux conservation. So you evaluate this flux on the left-hand side of the well, you get this, but this should be equal to the flux on the right boundary of the well, which is the same as the flux of a transmitted plane wave. So these three fluxes should be conserved and continuous at these two boundaries. And so I don't need to tell you how to calculate this flux inside the well or out of the well, so you can follow the same definition as before, and you can easily calculate this incoming flux, reflected flux, and the transmitted flux. So the next boundary condition is continuity of your wave functions and first derivative at these two boundaries. So in particular, it is sufficient to consider the ratio between these two quantities evaluated at these two boundaries. So you have this continuity of this u and du dx, and also so these quantities shows continuity at these two boundaries. So then you could take the ratio between this derivative and this u evaluated at these two sides of the boundaries, and first at this x equals minus a. So you could imagine that this ratio is evaluated right left of the boundary and also just right next to this the other side of the boundary. And you could also evaluate this ratio the other side of the boundary, which means that x equals to plus a. So you could evaluate this right inside this well, but next to this second boundary at x equals to a, and also evaluate it right to the other side of the boundary, but inside this potential step or out of the well. So you have this two different ratios. So for x equal to minus a, you get this continuity of this ratio, and you could simply just write down this equation very easily. So this is the same as k e to minus I, a minus I, k r e to the I, k a, and minus I, k a plus r to I, k a. And for x equals plus a, you get similar conditions. So you have how many equations? 1, 2, 3, 4, 5. So 5 relations, and you get 4 unknown. So you could uniquely determine A, B, and RT. So skipping details, so let me just write down this final answer for this capital R and T. So you could also look at your textbooks. Okay, so of course it takes some time to really derive such solutions, but it's a straightforward algebra, so there should be no problem. Good, so let's take a short break. When we come back, we will analyze the solutions, capital R and T, and in particular, we will make some remarks regarding special limits. For example, this capital E energy is much larger than the potential well, V0, what happens? Or E is actually almost 0, and what happens? Or there's some special value of the Q where there's no reflection and total transmission. And so what is going on here? So we will study special limits and looking at the solutions and understand what is going on. Let's take a short break. So even the simple potential well problem shows very interesting new quantum mechanical phenomena that doesn't exist in classical counterpart problem. Okay, so for example, if you consider a potential well for a classical, say, object like a ball or some classical object, and you could never imagine that your energy is above the ground floor and this particle could actually go backwards, get reflected. So let's look at special limits where this R and T shows some interesting phenomena. So first is when this energy is really, really high, much larger than V0. In that case, you get no reflection, only transmission. So which means that Q squared minus K squared is much less than 2KQ. So you get almost no transmission because Q squared and K squared are almost the same. So you get no reflection, but total transmission because K and Q are almost the same. So you can actually show that this is really equals to 1 if K is the same as Q. Just 30 more seconds. So the second is that when E goes to 0, you get total reflection, no transmission, because when E goes to 0, K goes 0, right? So when little k goes 0, you get no transmission but total reflection. So this is also expected because when energy is almost 0, and you get total reflection. So we will comment on this next time. But the third remark is that when there is a certain value of the little q here which satisfies the sign to QA vanishes, then this reflection vanishes because reflection is proportional sign to QA and you get total transmission. So this is so-called the transmission resonance, and this is the same quantum mechanical mechanism for the noble gas, so-called the neon light. So we will come back to this next time, that even though this energy E is not reaching the special value, but if this Q reaches the special value, then you get a total transmission and there's no reflection at all. So we will come on this problem next time, what is going on. So the short answer is that there are multiple total reflections inside this barrier, so that there is a destructive interference going on inside the barrier, so that it cancels all this reflective wave. And the wave can only go to the other side. So we will make comment on that. Okay, so these three are the special limits that we could pay attention, and something interesting and non-classical physics occurs. So that's it for today, and I'll see you on Wednesday.